So in this video, I wanted to talk a little bit about how we can think about potential energy, and power when we look at a simple circuit. Basically how we gain it and lose it for all three of these quantities. So I'm just going to use this really simple example of a circuit. In this chapter, we talked a little bit about resistors, which resist the current. You basically need to do that in order to have some sort of finite amount of current. You can't offer no resistance. And if you wanted to, if it made you feel more like applicable to real life, we could envision these two resistors as two different light bulbs, because that's essentially when we look at schematics and we have light bulbs in the circuit. In a sense, we're really treating those as inherent resistors that are attached to the circuit. This, of course, is the battery, and the battery has a potential difference across the terminals, and it's sort of the powerhouse of the circuit. It's allowing the current to flow through the circuit. This represents the positive terminal, this represents the negative terminal, and because we're using the convention of current flowing and being positive charges, even though they're not, that's not how the current works, but that's our convention. The current would come out of the positive terminal and then travel around the circuit until it got to the negative terminal. So the first thing that we're going to look at is sort of thinking about the potential differences that occur as we go around this circuit. And what's going to be helpful for us to do that, especially for the resistors, is to remember Ohm's law. Ohm's law says that the potential difference across a resistor is equal to the current times the resistance. So let's think about what's happening as we go through this circuit. Let's start with a battery. As we go from the negative terminal to the positive terminal of the battery, we are going to gain a potential. And so let's write that down, that we have a potential and this is what's gained. Now, as we go through the circuit, we go through resistors, and as the name resistor implies, they resist the flow of the current. And so as we go through each resistor, we're actually going to lose a certain amount of potential. We could think about it as the potential across resistor 1 and the potential across resistor 2. And so it turns out that the sum of these potential losses in terms of the magnitude is exactly equal to what we gain. That's the other thing about the circuit, is the idea is that it's a cycle, and sort of whatever we gain as we go through the circuit, we're going to have to eventually lose that. The idea is that we started with 0, and when we're done, we're going to end with 0. So again, if I think about this from the point of view of potential differences, as I go through the battery from the negative to the positive terminal, I'll gain potential V equal to the potential difference of the battery. Then I will travel through resistor 1, where I will lose a potential equal to V1, which actually could be calculated as the product of the current times that resistance. And then I'll go through resistor 2, lose potential 2, we named, which again would be equal to the current in the circuit, which is not changing, times the resistance of resistor 2. In the end, what we find is that we have gained some potential as we go through the circuit, and we also are going to lose it. Now, it might make more sense if I think about this transition in the terms of potential energy. Now, if you remember, potential energy can be expressed as a charge going through some potential difference, V, will experience a potential energy gain or loss, depending on if V is positive or negative, that is equal to the charge times the potential. So what if we thought about that from the point of view of our circuit once again? And so what we're going to think about is, the current is made up of charges. So what if we think of a little increment of charge that's going to pass across the potential, terminals of the battery, experiencing a potential difference, and we're going to kind of go all the way through and do that. And so as that little bit of charge goes through the battery, it gains a potential energy equal to the amount of that charge times the potential difference. So it got that potential energy. Now it's going to go through each one of these resistors, and we've already said that each of the resistors represents a potential difference that exists across each resistor. And also remember that those are losses. I'm not using positive and negative numbers in these expressions, but I'm trying to emphasize that on this side we're looking at losses, and on this side we're looking at gains. And so, again, my little charge that I named Q goes across the terminals of the battery and gains a potential energy of Q times V. Now, it will then continue through the circuit. It will lose a potential energy as it goes across resistor 1, because that was a potential drop. And that will be equal to Q times V1. And then it'll travel along and get to resistor 2, where it will experience another loss equal to Q times VT. Again, the idea being that we can also start to think about what's happening in terms of energy as we go across the circuit. The battery provides the potential energy, and the resistors dissipate the potential energy. Again, that name resistor kind of connotates, loss, negative things, and that's exactly what happens. They're resisting the flow or resisting the traveling of the current, and in order to get past that resistance, a little bit of energy needs to be expended. And that's why the potential energy is lost as we go through the resistors. Now, the fact that the amount of potential energy that is lost has to be equal to the potential energy is gained is simply because we imagine that if we get back to the starting point, we should be in the same situation that we were when we started, which was 0. Now, finally, let's think about power. Now, power, we've talked about that before. We talked about that first semester, and one way that we can think of it is the rate of energy use, in terms of the potential energy changes that occur over time. That makes it a rate. And so if you think about this in general, if we say power is the U over the time, and we just in general were calling the change in potential energy equal to Q times V, we're not using all the deltas just for simplicity's sake. So this represents a change in potential energy, and this represents a change in potential. But again, we're just getting rid of the deltas to be easier. So if we put that over time, notice that charge over time is a new quantity that we expressed or learned about in this chapter, which was current. So we actually end up thinking about the fact that power can be expressed as the current that passes through some potential difference. Now, I want to come up with the different expressions for power before we go back and look at the circuit. So far we say power can be expressed as I times V, but we could also use Ohm's law to write V as I times R, current times resistance, and that gives us I squared times R. And then I could also, down here, I could say, well, I might want to express it in different quantities. What if I replace the current using Ohm's law would be V over R times V, and that would be V squared divided by R. So in all, I have 3 different ways that I can express power. Power can be expressed as current times potential. It can be expressed as I squared R or V squared over R. It doesn't really matter which term or which expression you use, but sometimes different expressions seem to make more sense. For instance, if I'm looking at the power dissipated in a resistor, because that's exactly what the resistors do, we've already seen through these 2 examples that we're thinking about what is lost from the resistors. So going back to that, if I'm thinking about the power in the circuit that is dissipated through the resistors, it seems like it might make sense to use these 2 expressions. If I want to think about the power that's supplied by the battery, I don't know, I think it makes the most sense to use I times V. It doesn't make the other expressions wrong, but you just have to use them properly in order for it to make sense. So if we want to think about power in this circuit, again, we're going to sort of be practicing going through the circuit and thinking about how these different quantities change. I could say that when the current travels through the battery, this is going to be the expression for the power that is delivered to the circuit. And then I could think about the fact that every time now, as the current continues on through the circuit and travels through each resistor, there's going to be power dissipated. As I pass through each resistor. So again, I get power delivered as I travel through the battery, and as I go through the resistors, the power is dissipated, literally in the form of heat for the most part because of the resistance to the flow of the electricity. So I just wanted you to get used to different ways of thinking about what's happening as we go through the circuit. Having some of these things in mind will be helpful as we move on to the next chapters where we really get to apply some of this knowledge and really think about what's going on in a circuit.